so here so far we've talked about this system, and we started with that, the computer organization system. We talked about things like CPUs, ALUs. We talked about operating systems, okay? That the operating system, or the OS, okay, is in fact a program for management. Okay? And what does it manage? Well, it manages other programs. Right? That's how you can switch between Word and the internet when you're typing your essay, and you can check the latest things on Reddit. And as well, it manages resources on the computer, which includes hardware and data, which we could call files, for example. It manages the files on your computer, and it also manages the hardware, right? Make sure it works. OS as well has a few other features, a few little extras as well. Okay, we talked about that yesterday. Like one of the nice features that the OS can do is it can do networking. Right? Oh, I can connect my Windows machine to the internet. That's networking. I can connect my Mac to other Macs in the network and share files. I can connect it to a printer. That's great. So it can do networking. Okay? Some of them can do solitaire. Yeah, solitaires. And you get the idea. So there are other extra things built in. There's things like, not as big a deal anymore, but there's things like where you could defragment computers, and you could do disk cleanups and stuff like that, formatting and stuff like that. Those are some of the extras. So that's what the OS does, and I know for the most part you guys had a general knowledge about that, but you need to be ready to answer questions in that regard. Okay, so picking up where we left off yesterday, we were talking about that, and we were talking about other systems other than personal computers. So for example, mainframe computers. Mainframes and mini computers are machines that run multi-programming operating systems. Okay? Microcomputers, like personal computers, single users, okay, may or may not run multitasking operating systems. These run multitasking operating systems. You can do more than one thing at a time. But again, expand your knowledge beyond just a computer to any type of computing device. Some type of devices are single use. Right? Like the hardware built into like a GPS machine might not have multi-use capabilities. Older operating systems rely on something called batch mode processing, where each job is stacked up, and it performs one job, and when it's done, it goes to the next job. Okay? This is an older system. Okay? The so-called JCL, job control language, was used to kind of work with that system to give all the jobs a what's called batch processing system. Now, to say this is out of date is not accurate. There are still systems that use batch processing all the time. Again, we don't want to think of it as the computers you're used to. These computers are designed for multi-use. That's what they're marketed on. But there's more to this than this, right? There are actual, like in factories, machines that are running batch processing, right? And there are people being hired to program for these systems, okay, so that they can work. Then there's stuff like real-time operating systems, where you need processing to occur in real time. You can't sit there and wait for it to finish processing. An example might be airline reservation systems, where when a seat is booked on a flight, no one else can access that seat. So you could have 20 people at the counter booking flights on an airline. That has to happen in real time. Because, or if you think of like a bank, might be a good example. So if you have two people who have access to the same bank account, and they're across the city, and let's say you have $100 in your account, and both people try to draw $100 out at the same time, the bank should not allow that to happen. Whoever did it first should get the $100, and the other person should say, sorry, you can't do that. So that has to happen in real time. What would be another computer system that needs real-time processing? It's very crucial to happen in real time.
I guess if it went up like flights, it could be like flight control.
Flight control, yeah, that would be important. What else? Ticketmaster, yeah, so that two people can't buy the same ticket. Hospitals, absolutely. We'd have people hooked up to data, like actually seeing if they're alive or dead and stuff like that. Absolutely, you guys are on the right track. Okay? So here's that summary of operating system functions, right? Security also built into operating system. Who can do what? Who's on the system? Accounting, controlling resources, error handling, input outputs, interrupt handling. Okay? Interrupts are things like when the computer's doing something and it gets interrupted by something more important. Okay? Sequencing jobs, putting them into a order. Protection, security, creating a user interface for the people to work with. Allocating resources to, say, your peripherals. Executing software, managing memory. Operating system does a lot. Okay? Memory is a limited thing. So the operating system has to do a good job of managing it properly. Okay? We're going to talk more about memory in our unit on, there's actually a unit coming up that talks about that. It's a small unit, but it does talk about how memory is really managed in a much more concrete way. Okay? So just as a look ahead, there's things like virtual memory, which is we talked about yesterday, this idea of using hard drive space to create memory. In Windows, it usually calls this a swap file. Actually, if you have an older computer that's not working well, you'll often see this. You'll see in Microsoft Windows, all of a sudden this file show up that's huge. It's got this like huge amount of space being taken up. And it's only happening while you're running some programs. And then when you start up fresh, you notice this file isn't there anymore. Because that's that swap file that's being used to basically create RAM on the hard drive. Okay? Okay. Beyond the operating system's basic functions, it has a lot of little utility programs, like basic file operations, copy, paste, delete, rename, create folders. We take those for granted, but that's actually something the operating system has provided to you as a feature, as a utility that you can use. Okay? Backing up your hard drive, backing up your files. That's a feature, that's a utility that it provides. Formatting things like a USB. Maintaining your disk, like defragmenting, archiving, compression, which some of these are a bit older. You haven't maybe experienced these, because a lot of these are being done almost automatically for you now. But back in the early 2000s and the late 90s, our operating systems had these features, and people who use computers had to do them. I remember that was a big part was I would go around and defragment other people's computers so they'd work better. Okay? Virus checking is now built into a lot of these systems. Okay? These are not necessary for the operating system to work, so they're provided as utilities for that. Now, that being said, they're not always the best. Windows and Mac isn't necessarily the best at these utilities. So it may be that you buy software that performs a better job at virus protection or a better job at backing up data. Absolutely. But the operating system is still providing them to you as a feature. Okay? Here's some, again, some descriptions of these features, right? Like archiving is not something we do personally, but would be a big deal in organizations. If you work for an accounting firm, they need to keep that data. So legal firms as well, where they need to keep all that data, so they need a good system of archiving it to back up drives. So that just in case there's a fire in the legal firm, they have some copy of their data other than just the one that was in that building. Okay? Okay. Compression software. Have any of you ever heard of this program? WinZip? Okay. So what is compression software?
It removes repeating bits.
Okay, I need a simple explanation what compression software does. Okay? It's like a backpack. You've got all your books all laid out and you've got to go somewhere. You all shove them into one spot so you carry one thing around instead of all these multiple books all over the place. So compression software pushes all your stuff into one sort of spot. In doing so, it hopefully also optimizes the size. So your books or your data might have taken up a certain amount of space. By compressing it, it tries to reduce the amount of space it takes up. Compression also needs to be decompressed as well, okay, so that it can uncompress or like opening your backup and get it out there. In some cases, to compress something means you're going to have to sacrifice a little bit. A good example of this is images. When you take an image, it has all this data. It has every pixel has color in it and all kinds of good data in it. But the file size is too big. So you compress that file by converting it sometimes to a different format. A classic format might be the JPEG format. JPEG is an acronym, JPEG. Okay? Stands for Joint Photograph Experts Group, which was named after the group of programmers who figured out an algorithm that could take all that data and reduce it down. Okay? The same group also was a motion pictures expert group, which created what's called the MPEG format, okay? Which as well did the same thing. Some of this is what's called lost data when you do the compression, okay? Sometimes it's shortened to what's called lossy data. Formats that have that include JPEG and MPEG. They lose data. But the sacrifice is made so that you can save space, okay? So you can see here in the exam, they might talk about that. Like the MP3 format is a compressed, lossy data format where you know you're giving up some quality so that you have a smaller file so that you can fit it on your iPods and stuff like that. Okay? There are lossless formats which do not lose any data. You're going to get much higher quality, but in the end you're going to have a much larger file size. Okay. Here's an example. Here's a sentence. The brown cow jumped over the lazy dog. Could we compress that sentence? Okay. Well, the first thing you can do when you look at a sentence like this is you can look for patterns. Pattern recognition would be something you'd want. So one thing I can see is the word the occurs twice. Okay, but let's ignore that for now. Okay? And you should get back to work. Okay? Certain words like the could be represented by a single token. So we have the word the twice. Okay? Instead of storing the twice, we just say the word the is stored 2 times. Now again, let's say this sentence repeated itself 5 times. Now we can start to see a better compression because now we'd see the word the would be tokenized, so to speak. Okay? But we can go further than just the word, right? We can look for examples of just the letters OW appearing, or ED, or ER, right? And we start to see patterns within the text that could be tokenized and therefore compressed. How detailed we get into that would be based on the algorithm. At some point, though, we might end up losing some data. Like, for example, the fact that this is a capital T and that's a lowercase t. Maybe we ignore that fact. Then when we uncompress it, we lose the fact that that T was capitalized, maybe. We can accept that, maybe. We can accept that compression. Maybe we can't accept the compression that way. It depends on what you're writing it for, okay? So that's what happens when they deal with this stuff. I can give you another example. Actually, I think it's coming up, so we'll wait there for a second. Okay, viruses we know a little bit about. Viruses can range from ones that are fun to ones that are deadly. Actually, you guys probably haven't lived through the era of fun viruses as much as I have. But viruses back in the 90s were often written just for sort of fun purposes where people would just, I did it myself. I wrote viruses for friends of mine who had new computers, and I would say, here, do this. And then it would just sort of pretend like it wiped their hard drive and then just say, ha, ha, I got you. You know, kind of. I did that myself all the time, okay? Most viruses nowadays aren't that way. Most viruses nowadays don't want to be found out. They don't want to show off that they're a virus. They want to remain as hidden as possible, and they want to replicate themselves. In other words, like an actual biological virus, they spread from machine to machine. Okay? This includes words like Trojan horses, just like the history hides something going on behind the scenes, and there's payloads within them that does certain things. Most of viruses these days are designed for data mining. They want to find out information about you that they can sell or use. Okay? Here it talks about the function of a linker and a loader. This is actually a coding term. Links and loaders are essentially what your import statements do in your code, or your include statements in your code. They are connecting your code with another piece of code to put them together. In larger programs, this happens all over the place. It often links with stuff in the operating system. Certain types of files have library of code in them that you can connect to with your code to perform certain functions. Okay? Loaders are things that actually bring your program up so that it can be connected to the machine instruction cycle that we talked about before, so that it can load your data into the executable state. We're going to talk about states as well in an upcoming presentation. Okay, once an executable file has been generated, the actual thing is then created and put into the linker, so it links it together, checks any security that needs to go in, performs any functions it needs to do. So say it's your game, it's going to be linked in, it's going to be loaded up, okay? And then this might, as you guys know with your more complicated programming now, also be connected to files. So say your game is connected to a file that has game data file in it, or has high scores or something in it. So there's all kinds of linking to operating system resources, linking to your data resources, etc. And then it runs, okay? All right, so there's a lot of information on that slide. Most of it is, again, just general information about the way that these files are running within the operating system. Okay, let's just touch on this next topic before we wrap today. Here's what I wanted to get to today. We're going to define the terms bit, byte, binary, decimal, and hexadecimal. We already did some of this yesterday. I had you guys define bit and byte, okay? We're also going to outline the way data is stored on the computers. And here's what it says in the side notes. You need to include strings. How are strings stored? Integers, characters, and colors. Okay? This should include considering the space taken up by the data. For instance, the relationship between hexadecimal with colors and the number of colors available. Okay? There's a link to TOK if you're interested. You can look up what a lingua franca is if you want. It's a Latin term. Anyways, etc. So I'm just going to start this today because we have already started it. So I'm just going to refresh your memory. The simplest state a computer can be is the Boolean state. Okay? That on-off state, which we usually represent with a 0 or a 1. Okay? And that's what the computer is based on. So it's based on zeros and ones. Really, it's just ons and offs. Positive, negative, you could think of it that way. Okay? But if we're going to use the 0, 1, we then would want to move up to something like the integer. Okay? And we talked about that. We said, okay, well, this could be this. So if this is, and I'm going to use the term binary, which represents that, and this will represent decimal, which is the system we grew up with, right? 0, 1, 2, 3, 4, 10, a million, etc. This would represent 1. And then we went into, okay, well, what's 2 going to be? At this point, how do we get to 2? Well, I'll tell you, it's this. Whoops. No, it's not. It's this. Okay? What's 3? Well, it's this. Etc., etc., etc. How do I get to 197? So that's our challenge with the integer. Once we get past representing an integer, how do we represent real numbers, like doubles? How do we represent 197.532? How do we do that? Once we're finished with doubles, then what do we do? What's the next data type we need to represent? Well, no. Yeah, a character. We've already talked about that. For that, we'll just use binary and then use a table, a lookup table to look up all the characters. So that one maybe actually won't be as hard. And you guys remember what that table's called? Yeah, the ASCII table. How do we do strings? Yeah, it's just an array of this, which is binary from a table. Okay, so now it's all starting to come together. And that's our basic data types: Boolean, integer, double, character, string. And string we know is already a little more complex. String you actually already know in Java, not necessarily in C#, but in Java, is actually a class. And what you know about classes is a complex data structure built from the primitive data structures. And then we have classes that are built of classes, so everything builds off of the primitive data structures. And ultimately, all the primitive data structures build off of the binary data. Okay, so that's where we're going to go with this, is if we learn how to convert numbers into binary, we're on the right track. By the way, the easy answer to how it works here is it just takes two parts. The whole number portion and the decimal portion, and that turns both of these into binary and then finds a way to combine them together. So we're going to learn how that kind of works. No, it's nothing that complicated. It uses something called, have you guys heard of this in math class? The mantissa and the exponent. I know you've heard of the second part, the exponent. Have any of you heard of something called the mantissa before? Well, there's your fun lookup for class tomorrow. What is a mantissa? It's a math term. And we'll stop there today.